somewhere beyond the edge of everything you have ever known, a sphere of matter no wider than a city spins 500 times every second, sending beams of radiation sweeping across the cosmos like a lighthouse in the endless dark. It has been spinning for millions of years, and it will spin for millions more, long after every memory of Earth has faded into silence. Tonight, we explore the strangest objects that drift through the depths of space, things so bizarre that even our words struggle to describe them, and yet they exist, quietly, in the vast darkness between the stars. Welcome to Drowsy Discovery. Over the next 2 hours, over 100 gentle facts will float through this quiet space like distant starlight reaching your pillow. There is nothing to memorize, nothing to remember. Just listen and let your mind drift. Have you ever wondered what lies hidden in the spaces between galaxies, where light itself takes millions of years to travel? You are not alone. If these cosmic curiosities bring you peace, consider joining our growing family by subscribing and leaving a like, so that more restless minds might find their way here and drift into sleep among the stars. Now let your shoulders soften, let the weight of the day dissolve. The universe is vast and patient, and so is this night. There is nowhere else you need to be, nothing else you need to do. Let us begin. Black holes are not holes at all, but places where gravity swallows even light. Despite their name, black holes are not empty spaces or gaps in the fabric of reality, but rather regions where matter has collapsed so completely that gravity becomes inescapable, pulling everything inward, including the light that might otherwise reveal what lies within. When a massive star exhausts its fuel and can no longer resist its own weight, it crumples inward in a fraction of a second, crushing matter into a point so dense that the laws of physics, as we understand them, begin to break down. Nothing that crosses the boundary of a black hole can ever return, not signals, not particles, not even the faintest glimmer of light. They are invisible, yet their presence is felt through the way they bend the starlight around them, distorting the cosmos like a heavy weight pressed into fabric, darkness made permanent. Most large galaxies hide a supermassive black hole at their center. At the heart of nearly every large galaxy, including our own Milky Way, there lurks a black hole so massive that it weighs millions or even billions of times more than our Sun, sitting quietly at the cosmic center like a sleeping giant surrounded by billions of orbiting stars. These supermassive black holes did not form from the collapse of a single star, but grew over billions of years by swallowing gas, dust, and sometimes entire stars that wandered too close, accumulating mass with patient inevitability. The stars nearest to them move at tremendous speeds, whipping around in orbits that would take only years to complete, held captive by a gravity so intense that escape is unthinkable. Our own galactic center, known as Sagittarius A star, sits roughly 26,000 light-years from Earth, silent and dark, yet shaping the motion of everything around it, a quiet anchor in the turning spiral. The event horizon marks where escape from a black hole becomes impossible. The event horizon is not a physical surface you could touch or stand upon, but rather an invisible boundary where the pull of gravity becomes so overwhelming that even light, traveling at 300,000 kilometers per second, cannot climb back out, and anything that crosses this threshold is lost to the universe forever. From the outside, an object falling toward the event horizon would appear to slow down, its light stretching into ever longer wavelengths, reddening and dimming until it seems to freeze at the very edge of darkness, never quite vanishing but never quite arriving either. Yet from the perspective of the falling object itself, the crossing would happen in an instant, with no warning, no barrier, no sensation of passing through anything at all. The event horizon is a point of no return written not in stone, but in the fabric of space-time itself. One step, and the universe changes forever. Falling into a black hole would stretch time itself beyond recognition. Near a black hole, time itself bends and warps in ways that defy everyday experience, flowing at different rates depending on how close you are to the crushing gravity at the center, so that a clock falling inward would tick slower and slower compared to one watching safely from a distance. If you were to fall toward the event horizon while a friend watched from far away, they would see your descent stretch out across years, decades, perhaps centuries, your image lingering at the edge like a photograph slowly fading, while for you the journey might last only moments before the darkness closed in completely. This strange stretching of time is not an illusion, but a fundamental feature of the universe, predicted by Einstein and confirmed by every observation we have ever made. Time and space twist together near these objects in ways that make ordinary clocks meaningless. The closer you fall, the more the universe slows to watch. Some black holes spin so fast they drag space-time into a vortex. When a massive star collapses into a black hole, any rotation it possessed becomes concentrated into an ever smaller space, spinning faster and faster like a figure skater pulling in their arms, until the black hole whirls at speeds that would be unimaginable on Earth, dragging the very fabric of space-time around with it in a swirling vortex that nothing can resist. This effect, called frame dragging, means that near a spinning black hole, space itself is set into motion, pulled along by the rotation so that even standing still would be impossible, and you would find yourself swept into the spin whether you wished it or not. The region around such a spinning black hole, known as the ergosphere, is a place where energy can be extracted from the rotation itself, where the laws of physics twist in unfamiliar ways. It is gravity dancing, space turning, the cosmos in perpetual motion. Stillness ceases to have meaning. At the heart of every black hole may lie a singularity of infinite density. Deep within every black hole, hidden behind the event horizon where no light can escape and no message can be sent, there may exist a point where all the mass that has fallen inward is compressed into an infinitely small space, a singularity where density becomes infinite and the ordinary rules of physics cease to function. At such a point, the equations that describe gravity and spacetime produce answers that are no longer meaningful, infinities that hint at something our current understanding cannot grasp, a place where the fabric of reality itself may be torn or transformed in ways we cannot yet imagine. No one has ever observed a singularity directly, and perhaps no one ever will, for they are forever shielded behind horizons that permit no signal to escape. Whether they truly exist as points of infinite density or whether nature has some other structure waiting to be discovered remains one of the deepest mysteries of astrophysics, a question hiding at the heart of darkness. And yet, in the strange mathematics of the cosmos, even black holes may not be eternal, for they slowly whisper themselves away into the silence. Black holes slowly evaporate, whispering radiation into the void for eons. Although black holes are famous for swallowing everything that comes near, they are not truly eternal, for at the very edge of their event horizons, a subtle process is at work, a faint whisper of particles escaping into the cosmos and carrying energy away, so slowly that a black hole, the mass of our sun, would take longer than the age of the universe multiplied countless times to fade completely. This radiation, named after the physicist Stephen Hawking who predicted it, arises from the strange behavior of empty space near the event horizon, where pairs of particles flicker into existence and are torn apart by gravity, one falling in and the other escaping to carry the black hole's energy outward. Over inconceivable stretches of time, this process will shrink every black hole, first to a glowing ember, then to a final burst of radiation, and finally to nothing at all, leaving behind only empty space where once there was absolute darkness. Even the darkest objects are not forever. Even silence eventually fades. Primordial black holes may be smaller than an atom, yet heavier than a mountain. In the earliest moments after the Big Bang, when the universe was a seething ocean of energy and matter far denser than anything we see today, tiny regions of space may have collapsed under their own weight to form black holes no larger than an atom, yet containing the mass of entire mountains or even planets, packing billions of tons into a space smaller than the nucleus of a single cell. These primordial black holes, if they exist, have been drifting through the cosmos ever since, invisible and silent, too small to swallow anything significant yet too massive to be ignored, their gravity subtly bending the light that passes near them. Some scientists believe they could account for the mysterious dark matter that seems to fill the universe, while others search for evidence of them evaporating in tiny bursts of radiation. They remain theoretical, never confirmed, yet too compelling to dismiss. The smallest, and perhaps the oldest mysteries of all. Intermediate mass black holes remain among the deepest mysteries of astrophysics. Between the small black holes born from dying stars and the supermassive giants lurking at galactic centers, there exists a puzzling gap, a range of masses where black holes should exist, but have proven frustratingly difficult to find. These intermediate mass black holes, weighing anywhere from hundreds to hundreds of thousands of solar masses, are predicted by theory but rarely confirmed by observation, hiding perhaps in the dense cores of star clusters or wandering alone through the darkness between galaxies. Their scarcity raises questions about how black holes grow, whether they merge gradually over time or leap in size through sudden collisions, and whether our models of stellar evolution are missing something fundamental. A few candidates have been detected through gravitational waves or faint X-ray emissions, yet their nature remains uncertain, hovering at the edge of what we can reliably measure. They are the missing link in a cosmic family tree, elusive, uncertain, waiting to be found. Two merging black holes release more energy than all the stars combined. When two black holes spiral toward each other and finally collide, the energy released in that final moment exceeds the combined light of every star in the observable universe, an output so vast that it is difficult to comprehend even in the language of astronomy, yet almost none of it escapes as light or heat. Instead, the energy pours outward in the form of gravitational waves, ripples in the fabric of spacetime that spread across the cosmos at the speed of light, passing through planets and stars and galaxies without being absorbed, carrying the signature of the collision to any detector sensitive enough to listen. In that brief instant, the two black holes become one, their event horizons merging, their masses combining, their spins rearranging into a new and larger darkness. The event lasts only a fraction of a second, yet it reshapes space-time across billions of light years. The universe shivers and then is still again. Black hole collisions send gravitational waves rippling through space-time itself. Every time two black holes merge somewhere in the distant universe, they send ripples through the very fabric of space-time, waves that stretch and squeeze everything they pass through by amounts so tiny that measuring them requires the most sensitive instruments ever built, laser beams bouncing between mirrors kilometers apart, searching for distortions smaller than the width of a proton. These gravitational waves were predicted by Einstein over a century ago, but it took until 2015 for the first detection to be confirmed, opening a new way of observing the cosmos, one that does not rely on light at all, but on the trembling of space itself. Since then, dozens of mergers have been heard, each one a whisper from the deep past, carrying information about objects that collided billions of years before the Earth was formed. They travel unchanged across the cosmos, passing through matter as if it were not there. The universe is ringing, and now we can listen. Beyond the realm of black holes, there exist objects just as dense, yet they shine with the fierce light of creation rather than the silence of absolute darkness. A teaspoon of neutron star would weigh more than 1 billion tons on Earth. When a massive star collapses, but stops just short of becoming a black hole, the matter at its core is crushed so completely that protons and electrons merge into neutrons, packing the mass of 500,000 Earths into a sphere no wider than a city, so dense that a single teaspoon of its material would weigh more than 1 billion tons if placed upon our planet's surface. The gravity on such a star is so intense that climbing a mountain only a few millimeters tall would require more energy than a human could produce in a lifetime, and light itself bends noticeably as it passes by. If you could somehow stand on a neutron star, you would be crushed flat in an instant, your atoms pressed into a thin smear across its impossibly smooth surface. These objects spin, pulse, and radiate energy across the cosmos, visible from billions of light years away. A city-sized ember burning with the fury of 1 million suns. Neutron stars are so smooth that their tallest mountains are mere millimeters high. The surface of a neutron star is the smoothest known in the universe, so perfectly flattened by the immense gravity that any imperfection, any bump or ridge that might be called a mountain, rises no more than a few millimeters above the surrounding crust, a height less than the thickness of a coin, yet representing the absolute maximum that matter can resist being pulled flat by forces beyond imagining. The crust itself is made of material far stronger than any metal on Earth, held together by the nuclear forces that bind matter at its most fundamental level. Yet even this is not enough to support significant variation against the pull of a gravity billions of times stronger than our own. If you could run your hand across the surface, you would feel nothing but perfect smoothness, no texture, no grain, just the faint warmth of a surface glowing with X-ray light. It is a world pressed flat by its own weight, perfectly, impossibly still. Some neutron stars spin hundreds of times every second. When a massive star collapses into a neutron star, the conservation of angular momentum causes any rotation the star once had to accelerate dramatically, so that a neutron star can whirl around its axis hundreds of times every second, its surface moving at a significant fraction of the speed of light, yet held together by gravity so powerful that not a single atom can escape. The fastest of these spinning neutron stars, called millisecond pulsars, complete a full rotation in just a few milliseconds, their magnetic poles sweeping beams of radiation across the cosmos like lighthouses spinning faster than the eye could ever follow. These objects are so stable in their rotation that they rival atomic clocks in precision, marking time with a regularity that seems almost mechanical. Their spin carries them through the ages, slowly losing energy but remaining remarkably constant across millions of years, time measured in pulses of light. Pulsars sweep beams of radiation across the cosmos like cosmic lighthouses. Pulsars are rapidly spinning neutron stars that emit intense beams of electromagnetic radiation from their magnetic poles. And because these poles are often misaligned with the axis of rotation, the beams sweep through space like the light from a lighthouse, appearing to pulse on and off as they pass through our line of sight, sometimes hundreds of times each second. When the first pulsar was detected in 1967, its signal was so regular that astronomers briefly wondered whether they had discovered a message from an alien civilization, and they nicknamed it LGM-1 for Little Green Men before the true nature of the signal was understood. Since then, thousands of pulsars have been found across the Milky Way, each one a beacon marking the presence of a collapsed star, its radiation carrying information about the extreme conditions near its surface. Some are solitary, others orbit companions, but all of them whisper across the galaxy in pulses of light and radio waves, a heartbeat in the dark. And as these strange objects spin silently in the dark, there is no need to hold on to every detail. Let the facts drift past you like distant stars, softly, gently. Take a breath if you wish, and let your body settle deeper into rest. A magnetar could erase a credit card from halfway across the solar system. Magnetars are a rare type of neutron star possessing the most powerful magnetic fields in the known universe, so intense that they could strip the data from a credit card from a distance half as great as that between the Sun and Jupiter, warping atoms into elongated shapes and disrupting any electronic device utterly and completely. These fields are 1,000 trillion times stronger than the magnetic field of Earth, strong enough to alter the energy states of electrons in ways that make ordinary chemistry impossible, creating conditions that exist nowhere else in the observable cosmos. A magnetar's surface is constantly stressed by the struggle between its magnetic forces and its own immense gravity, occasionally cracking in violent starquakes that release bursts of gamma rays visible from across the galaxy. These objects are rare, short-lived, and immensely dangerous, though the nearest known magnetar is safely far from Earth, power concentrated beyond comprehension. Magnetar fields are 1,000 trillion times stronger than Earth's own. The magnetic field of a magnetar is so overwhelmingly powerful that it defies comparison with anything we experience on Earth, reaching strengths a quadrillion times greater than the field that gently nudges a compass needle toward the North Pole, strong enough to distort the shapes of atoms themselves and to polarize the vacuum of empty space in ways that blur the boundary between matter and energy. At such intensities, light bends and splits, passing through the magnetized vacuum in ways that depend on its polarization, creating optical effects that exist nowhere else in nature. The field decays over time, losing its intensity across thousands of years until the magnetar becomes an ordinary neutron star, its fury spent, its power faded. While it lasts, however, it dominates the space around it utterly, shaping the behavior of matter and radiation in ways that stretch our understanding of physics, a force beyond any terrestrial scale. Magnetar starquakes release more energy in 1/10 of a second than our Sun does in 100,000 years. The crust of a magnetar is under constant tension, stressed by the immense magnetic field that threads through it, pulling and warping the dense nuclear matter, until, occasionally, the crust fractures in a sudden, violent event called a starquake, releasing more energy in a fraction of a second than our Sun will produce over 100,000 years. These events send bursts of gamma radiation streaming across the cosmos, powerful enough to disturb Earth's atmosphere even from tens of thousands of light years away, as happened in 2004 when a magnetar in the constellation Sagittarius briefly ionized our upper atmosphere with a flash lasting just 0.2 of a second. The starquake itself represents only a tiny rearrangement of the crust, a shift of perhaps a few centimeters, yet the energy involved is almost beyond comprehension. After the quake, the magnetar settles, waiting, its crust slowly building stress again until the next release, a world that cracks under its own power. And from the ultramagnetic to the ultra-strange, the universe presents us with stellar remnants that challenge everything we think we know. Strange stars may be made entirely of dissolved quarks. Deep within the most extreme stellar remnants, matter may be compressed so thoroughly that even neutrons break apart, their constituent quarks freed from the bonds that normally confine them, merging into a sea of quarks that flows without the structure we associate with ordinary particles, forming a substance called strange matter that includes a third type of quark rarely seen elsewhere in the universe. If such strange stars exist, they would look superficially like neutron stars, spinning rapidly and emitting radiation, yet their internal structure would be utterly different, a single gigantic nucleus rather than a collection of individual particles pressed together. Some theories suggest that strange matter might be the true ground state of all matter, more stable than ordinary atoms, and that a single grain of it could convert everything it touched into more of the same. Whether these objects are real or merely theoretical remains uncertain. The universe may harbor secrets held together by forces we have only begun to imagine. Quark stars would occupy the strange middle ground between matter and the abyss. If matter can be compressed beyond the density of neutron stars without collapsing into a black hole, then quark stars may represent the final stable state before the ultimate darkness, objects where quarks roam freely in a soup of the most fundamental particles we know, unconfined by the usual rules that bind them into protons and neutrons. Such a star would be denser than a neutron star, but smaller, its surface glowing with radiation in ways that might reveal its exotic interior if only we knew exactly what to look for. The existence of quark stars remains unproven, with some candidate objects showing properties that do not quite fit the neutron star model, leaving room for speculation and wonder. They would be bridges between the matter we understand and the unknown realms beyond, places where ordinary physics reaches its limits, a shore at the edge of the abyss. Prion stars could be smaller than an atom, yet weigh as much as a mountain. Some theories in particle physics suggest that quarks themselves may be made of even smaller components called prions. And if this is true, then matter could potentially be compressed far beyond the density of quark stars into objects so compact that they would be smaller than an atom, yet contain the mass of a mountain. 1 billion tons packed into a space 1 trillion times smaller than the width of a human hair. These hypothetical prion stars have never been observed and may not exist at all, yet they represent the logical endpoint of compression, the question of just how small matter can be squeezed before collapsing into a black hole. If they do exist, they would be nearly undetectable, too small to see, too massive to ignore, drifting silently through the cosmos like invisible anchors of density beyond imagination. They remain firmly in the realm of speculation, a thought experiment at the frontier of what physics allows, smallness carried to its ultimate extreme. Electroweak stars convert matter into radiation under Big Bang conditions. In the first moments after the Big Bang, when the universe was unimaginably hot, the electromagnetic and weak nuclear forces were unified into a single electroweak force, a state of matter that has not existed naturally since, except perhaps at the cores of certain dying stars, where temperatures and densities reach values so extreme that the conditions of the earliest cosmos are briefly recreated. An electroweak star would be a collapsing object hovering at the edge of becoming a black hole, held up temporarily by the energy released as quarks are converted into leptons under these extraordinary conditions, a process that transforms matter directly into pure radiation with almost perfect efficiency. Such a star would shine with a brilliance that outstrips ordinary supernovae, burning through its remaining fuel in a cosmic instant before finally succumbing to gravity and becoming a black hole. Whether any such objects have ever existed remains theoretical, a bridge between astrophysics and particle physics waiting to be crossed. A brief fire recreating the beginning of time. Thorn-Zitkow objects are neutron stars living inside red supergiants. Imagine a neutron star, that impossibly dense remnant of a collapsed giant, spiraling inward into the bloated atmosphere of a red supergiant and settling at its core, a city-sized object of nuclear matter nestled within a star hundreds of times wider than our Sun, the two objects merging into a single hybrid structure unlike anything else in the cosmos. These Thorn-Zitkow objects, named after the physicists who first proposed them, would look outwardly like ordinary red supergiants, but their internal structure would be profoundly different, powered by the neutron star at the center, fusing elements in ways that produce unusual chemical signatures detectable in the star's spectrum. At least one candidate has been identified, a red supergiant with an unusual abundance of certain elements that cannot easily be explained by normal stellar processes. If confirmed, it would represent one of the strangest marriages in the universe. Two deaths becoming one bizarre, lingering life. And if the strange remnants of dead stars were not enough, some stars defy death altogether, rising again when they should have faded into darkness. Zombie stars reignite by stealing matter from nearby companions. When a white dwarf, the cooling ember of a sun-like star that has exhausted its fuel, finds itself orbiting close enough to another star, it can begin to siphon material from its companion, drawing gas across the gap between them and accumulating fresh hydrogen on its surface, until eventually the pressure and temperature become sufficient to reignite nuclear fusion in a sudden flash that makes the white dwarf shine brightly again. These zombie stars, sometimes called recurrent novae, can flare up multiple times over the centuries, their periodic outbursts lighting up the sky before fading back into comparative dimness, repeating the cycle as long as their companion star has material to give. In some cases, the accumulated mass can push the white dwarf over a critical threshold, triggering a far more violent explosion known as a Type Ia supernova, which utterly destroys the white dwarf and outshines entire galaxies for a brief, brilliant moment. They are stars that refuse to stay dead, drawing life from the unwilling, resurrection through theft. Some white dwarfs spin so fast they are on the verge of tearing apart. White dwarfs are the dense, Earth-sized remnants of sun-like stars, and while most spin slowly and peacefully, some have been found whirling around their axes so rapidly that they complete a full rotation in mere seconds, their surfaces moving at speeds so great that only the extreme gravity holding them together prevents them from flying apart. These rapidly spinning white dwarfs are often found in binary systems, where the transfer of material from a companion star has added angular momentum over time, spinning them up like a top being whipped faster and faster. The fastest known specimens rotate in just about 25 seconds, a speed that would seem dizzying for an object the size of a planet, yet they hold together, their immense density keeping every atom firmly in place against the outward pull. They are the aging embers of once great stars, still dancing long after their fires have faded. A final, furious spin before the stillness of eternity. A white dwarf fits the mass of our Sun into a sphere the size of Earth. When a star like our Sun exhausts its nuclear fuel and sheds its outer layers, the core that remains is a white dwarf, an object containing roughly the same mass as the Sun compressed into a volume no larger than our planet, so dense that a teaspoonful would weigh several tons if brought to Earth's surface. The matter inside is supported not by the heat of fusion, which has long since ended, but by a quantum mechanical effect called electron degeneracy pressure, the resistance of electrons to being squeezed too closely together, a property of matter that arises from the deepest laws of physics. A white dwarf is born hot, glowing with the residual heat of its former life as a star, but over billions of years it slowly cools, fading from white to yellow to red, and eventually, in theory, to black, though the universe is not yet old enough for any black dwarf to exist. It is a star's quiet retirement, a slow fade into the endless night. The oldest white dwarfs are nearly as old as the universe itself. Because white dwarfs cool so slowly, radiating their heat into space over billions of years, the coldest and dimmest among them are fossils from the earliest epochs of the cosmos, objects that formed not long after the first generation of stars ignited and have been fading ever since, carrying within them information about conditions that existed before the Earth, before the Sun, before most of the galaxies we see today. By measuring the temperature and luminosity of these ancient embers, astronomers can estimate their ages, and by extension, the age of the stellar populations they belong to, using them as cosmic clocks that record the passage of time more faithfully than almost any other object. Some of the oldest known white dwarfs are found in globular clusters, dense swarms of ancient stars that orbit the Milky Way like relics of a younger universe. They are time capsules, still glowing with the faint memory of fires that burned when the cosmos itself was young, witnesses to the beginning. Black dwarfs will one day exist, but the universe is not yet old enough. As white dwarfs cool over unimaginable stretches of time, they will eventually radiate away all their remaining heat, fading from dim embers into completely cold, dark spheres of degenerate matter, objects called black dwarfs that emit no light whatsoever and can be detected only by their gravitational influence on anything that passes nearby. The process of cooling to this final state takes so long, however, trillions of years by some estimates, that the universe at just under 14 billion years old is far too young for any black dwarf to have formed yet, making them theoretical endpoints rather than observed realities. When they do finally appear, they will mark the ultimate fate of most stars, cold and silent and utterly dark, drifting through a cosmos that will itself be approaching its final stages of expansion and stillness. They are the future graves of suns, a darkness that has not yet arrived. And as stars fade towards silence, others blaze with ferocity that defies comprehension, outshining entire galaxies from the edge of the observable universe. Quasars can be seen from billions of light-years away. Quasars are among the most luminous objects in the entire universe, shining with such intensity that they can be seen from distances spanning billions of light-years, their light traveling across the cosmos for so long that it shows us the universe as it was when galaxies were still young and the first structures were just beginning to form. At the heart of every quasar lies a supermassive black hole actively devouring matter, drawing gas and dust into an accretion disk that heats up to millions of degrees as it spirals inward, releasing vast amounts of energy across the entire electromagnetic spectrum before the matter vanishes behind the event horizon forever. These objects were more common in the early universe, when galaxies were smaller and collisions more frequent, feeding their central black holes with abundant material, and they have grown rarer as the cosmos has aged and settled into a quieter state. They are beacons from the distant past, markers of a more violent era, light that remembers what we cannot. A single quasar can outshine 1 trillion suns from a region no larger than our solar system. The luminosity of a quasar is almost impossible to comprehend, with the brightest examples pouring out more light than 1 trillion stars like our Sun, all from a region of space centered on the supermassive black hole at the galactic core, an area that would fit comfortably within the orbit of Neptune, yet outshining the combined glow of hundreds of billions of ordinary suns. This staggering output comes from the accretion disk, a swirling platter of superheated gas that converts gravitational energy into radiation with an efficiency far exceeding any nuclear reaction, so that a quasar can release more power by letting matter fall toward its black hole than a star produces by fusing hydrogen into helium. Early astronomers mistook them for stars within our own galaxy because they appeared as point-like sources of light, only later realizing that their redshifts placed them at cosmological distances, making them unimaginably powerful. They are the brightest steady lights in the universe, furnaces burning at the edge of oblivion. Blazars point their jets of energy directly at Earth. Blazars are a special type of active galactic nucleus, where one of the powerful jets of matter and radiation shooting out from near the central black hole happens to be aimed almost directly at Earth, so that we look straight down the barrel of a relativistic beam traveling at nearly the speed of light, its brightness amplified by the motion toward us in a phenomenon called relativistic beaming. Because the jet is pointed our way, the light and radiation reaching us appears far more intense than it would from any other angle, making blazars among the most variable and violent-looking objects in the sky, capable of changing brightness dramatically over days or even hours as the beam shifts and fluctuates. Despite the term violent, there is no danger, for these objects lie billions of light-years away, their beams spreading harmlessly across the cosmos before the faintest traces reach our telescopes. They are cosmic spotlights trained on us by chance, revealing the hidden fury of distant galaxies, a lucky alignment illuminating the depths. Blazar jets pierce through intergalactic space for millions of light-years. The jets that blaze outward from active galactic nuclei are not confined to the galaxy that hosts them, but can extend far beyond, punching through the intergalactic medium for millions of light-years. Narrow beams of particles and radiation that retain their coherence across distances that dwarf entire galaxies. These jets are powered by magnetic fields twisting near the event horizon of the central black hole, somehow channeling matter and energy into collimated streams that travel at nearly the speed of light, their particles spiraling along magnetic field lines and emitting radiation across the electromagnetic spectrum. The largest jets span distances greater than the separation between the Milky Way and Andromeda, shaping the space around them, heating the gas between galaxies, and influencing the formation of stars and planets in regions where no earthly telescope could see them directly. They are threads of energy woven across the void, linking the infinitely small to the cosmically vast, lines drawn between the darkest points in the universe. Radio galaxies emit lobes of radio waves larger than the galaxies themselves. Radio galaxies are observed to have enormous lobes of radio-emitting plasma extending from their cores, inflated by the jets of particles streaming out from the central black hole, clouds of energetic matter that glow not in visible light, but in radio waves, stretching across space for distances that often exceed the size of the host galaxy itself. These lobes can span millions of light-years and contain enough energy to rival the entire luminous output of ordinary galaxies, yet they emit almost no light that human eyes could see, revealing themselves only to radio telescopes tuned to the long wavelengths where they shine most brightly. They form over millions of years, as the jets push against the intergalactic medium, inflating bubbles of hot plasma that slowly fade as the particles lose energy and dissipate into the cosmic background. They are the slow exhalations of supermassive black holes, breath made visible across unimaginable distances, whispers carried on radio waves. And in the fleeting moments between silence and storm, the cosmos erupts with bursts of energy so brief and violent that they reshape our understanding with every detection. Gamma-ray bursts release more energy in seconds than our sun will in its entire lifetime. Gamma-ray bursts are the most violent explosions in the universe, releasing more energy in a few seconds than our sun will produce over its entire 10 billion-year lifetime. Their gamma radiation streaming outward in beams that, if pointed toward Earth, would be visible from halfway across the observable universe. They come in two varieties: long bursts lasting more than 2 seconds, typically associated with the collapse of massive stars, and short bursts lasting less than 2 seconds, thought to result from the merger of compact objects like neutron stars, both marking the births of black holes in cataclysms of unimaginable power. For their brief duration, a gamma-ray burst can outshine entire galaxies, though the light is concentrated in gamma rays that strip electrons from atoms and would be lethal to any life caught nearby. Fortunately, the nearest known bursts lie safely far from Earth, distant flashes illuminating the violence hidden in the cosmos, a death cry that outshines everything. Some gamma-ray bursts mark the explosive birth of black holes. When a massive star reaches the end of its life and its core collapses, it can produce a long gamma-ray burst, a jet of gamma radiation that punches through the collapsing stellar envelope and streaks outward at nearly the speed of light, signaling the exact moment that a new black hole comes into existence at the heart of the dying star. This birth is accompanied by a supernova, or in the most extreme cases a hypernova, explosions that disrupt the outer layers of the star and scatter newly forged elements across space, seeding future generations of stars and planets with the raw materials of chemistry. The gamma-ray burst itself lasts only seconds to minutes, but the afterglow, as the jet collides with surrounding material, can be observed for weeks in X-rays, optical light, and radio waves. They are announcements from the cosmos, news of black holes being born in fire, the first cries of the darkest objects. Fast radio bursts flash for milliseconds from billions of light-years away. Fast radio bursts are among the most mysterious phenomena in modern astronomy, intense pulses of radio waves that last just a few milliseconds, yet carry as much energy as our sun releases in an entire day, arriving from sources so distant that their light has been traveling for billions of years before reaching our radio telescopes on Earth. First detected in 2007, these bursts puzzled scientists because they appeared to be extragalactic yet incredibly brief, leaving almost no time to study them before they vanished, and for years the causes remained completely unknown. Gradually, evidence has pointed toward magnetars and other extreme objects as the likely sources, though the precise mechanisms remain under investigation. Each detection refines our understanding, bringing us closer to solving one of the youngest mysteries in astrophysics: a flash, a silence, and 1,000 questions. Some fast radio bursts repeat, while others flash only once and vanish forever. Among the most intriguing aspects of fast radio bursts is that some of them repeat, flashing multiple times from the same location over days, weeks, or months, while others are seen only once and are never detected again, no matter how long astronomers watch and wait. The repeating bursts suggest sources that survive the emission process, perhaps magnetars releasing energy in sudden starquakes or other processes that can happen more than once, while the non-repeating bursts might come from catastrophic events like the collapse of a neutron star or the disruption of a star by a black hole, processes that destroy the source in the act of creating the signal. The distinction between repeaters and one-time events has led to speculation that there may be multiple types of fast radio bursts arising from different physical mechanisms, or perhaps we simply have not watched long enough to catch the repeats. The universe keeps its secrets, revealing them one flash at a time, patience rewarded by milliseconds of light. Soft gamma repeaters are magnetars cracking under unimaginable magnetic pressure. Soft gamma repeaters are magnetars that periodically release bursts of gamma rays and X-rays, flashes that arise when the immense magnetic stresses on their crusts become too great and the surface fractures in a starquake, releasing trapped energy in sudden outbursts that can repeat irregularly over months or years. Unlike the gamma ray bursts from distant galaxies, soft gamma repeaters are found within the Milky Way or its nearest neighbors, close enough that their bursts can temporarily affect Earth's upper atmosphere, as happened in 2004 when a magnetar in the constellation Sagittarius briefly ionized our planet's ionosphere. The crust of a magnetar is incredibly strong, yet even it cannot resist forever the forces exerted by the magnetic field, and each crack releases a fraction of the stored energy, sending waves of radiation across space. These restless objects remind us that the dead stars populating our galaxy are not always silent. Sometimes they stir and the cosmos trembles. X-ray binaries glow with deadly radiation as one star devours another. X-ray binaries are pairs of stars locked in an intimate gravitational dance, one a compact object like a neutron star or black hole, the other an ordinary star close enough that material is stripped from its surface and pulled toward the dense companion, forming an accretion disk that heats to millions of degrees and emits intense X-ray radiation visible from across the galaxy. The transfer of mass powers these systems, turning gravitational energy into light with an efficiency far greater than ordinary stellar fusion. And the X-rays they emit carry signatures of the extreme conditions near the central object, revealing properties of neutron stars and black holes that would otherwise remain hidden. Some X-ray binaries flare dramatically as blobs of overheated gas spiral inward, while others shine steadily for years, their accretion disks fed by a constant stream of stolen matter. They are cosmic vampires, draining their companions to glow with stolen light, a slow feast recorded in X-rays. Microquasars shoot jets of matter outward at nearly the speed of light. Microquasars are X-ray binaries that produce narrow jets of plasma shooting outward from the region near the compact object, miniature versions of the powerful jets seen in quasars, but scaled down to stellar sizes, moving at significant fractions of the speed of light, and often appearing to travel faster than light due to relativistic projection, effects that confuse our sense of distance and motion. These jets are thought to arise when magnetic fields near the accretion disk become twisted and channel material upward and outward in twin beams, a process that remains imperfectly understood but clearly capable of accelerating matter to extreme velocities. Observing microquasars allows astronomers to study the same physics that operates in distant quasars, but on timescales compressed from millions of years to days or hours, making them valuable laboratories for understanding how jets form and evolve. They are quasars in miniature, the same fury at a smaller scale, a demonstration of universal mechanics. And as the cosmos flashes and fades, you remain here, safe and still. Let your breath slow. Let your thoughts become like the quiet moments between one pulse of light and the next. There is no hurry. Hypervelocity stars are ejected from galaxies at millions of kilometers per hour. Hypervelocity stars are stellar outcasts, flung from their home galaxies at speeds so extreme that they escape the gravitational pull entirely, racing through intergalactic space at millions of kilometers per hour, with no hope of ever returning to the galactic neighborhood where they were born. Most are thought to originate from close encounters with the supermassive black hole at the galactic center, where a binary star pair is torn apart by tidal forces, one star captured or destroyed, while the other is whipped outward with tremendous velocity, carrying the energy of the encounter with it across the cosmos. These runaway stars carry the chemical signatures of their origin, providing clues about the populations of stars near the galactic core, even as they streak toward the intergalactic void. Some will travel for billions of years, crossing vast stretches of emptiness, forever alone in the darkness between galaxies, exiles with no destination. Rogue stars wander alone through the darkness between galaxies. Between the galaxies, in the vast gulfs where light takes millions of years to cross, there drift rogue stars, solitary suns that have been stripped from their parent galaxies by gravitational interactions, galactic collisions, or close encounters with massive objects, now wandering alone through a void so empty that their nearest neighbors may be millions of light years away. These intergalactic wanderers carry on burning, fusing hydrogen in their cores just as they would within a galaxy, but with no companions, no planets we know of, nothing to witness their light, except whatever faint dust and gas might drift through their vicinity. They represent a significant fraction of all the stars in the universe, hidden from easy observation because they are scattered so thinly across such immense volumes. If any of them have planets, those worlds orbit in almost perfect isolation, suns burning in the darkness, utterly alone. And not only stars wander through the cosmic wilderness, for there are entire worlds adrift without suns, wandering through eternal night. Rogue planets drift through space without any star to orbit. Scattered throughout the galaxy are planets that belong to no star, worlds ejected from their original solar systems by gravitational disturbances or formed in isolation from collapsing clouds of gas, now drifting endlessly through the interstellar darkness with no sun to warm them and no orbit to define their path. These rogue planets far outnumber the stars themselves by some estimates, billions upon billions of dark worlds wandering invisibly through the Milky Way, detectable only when they pass in front of a distant star, and their gravity briefly magnifies the background light. Without a star, their surfaces are frigid, exposed to the background temperature of the cosmos, just a few degrees above absolute zero, though some may retain warmth beneath thick atmospheres or from radioactive decay in their cores. They are orphans of planetary formation, lost to the void, carrying whatever secrets their surfaces hold through an endless night, worlds without sunrise. Some rogue planets may harbor liquid water beneath their frozen surfaces. Even without a star to warm them, some rogue planets may maintain subsurface oceans of liquid water, kept warm by the decay of radioactive elements in their interiors or by gravitational tidal heating if they retain massive moons, creating environments where, in theory, life might be possible far from any sunlight. These hidden oceans would be sealed beneath kilometers of ice, insulated from the cosmic cold, their waters circulating slowly in the darkness, carrying whatever chemistry the planet's formation bequeathed to them. On Earth, life thrives in deep ocean vents far from sunlight, suggesting that solar energy is not strictly necessary for biology, And if similar processes operate on rogue planets, then the galaxy may host far more habitable environments than the count of stars would suggest. It is a strange thought that life might flourish on worlds adrift between the stars, never knowing day or night, hidden waters in the endless dark. Oumuamua passed through our solar system in 2017 with unexplained acceleration. In 2017, astronomers detected an object falling through our solar system from interstellar space, a traveler from beyond the sun's dominion named Oumuamua, meaning scout or messenger in Hawaiian, tumbling through the inner planets before being flung back into the void from which it came. What made this visitor so puzzling was not only its origin but its behavior, for as it passed the sun, it accelerated slightly in a way that could not be explained by gravity alone, as if something was pushing it, perhaps outgassing from its surface as it warmed, perhaps a property of its unusual shape, or perhaps something altogether stranger. Its shape itself remained mysterious, appearing elongated far beyond any known comet or asteroid, yet producing no visible coma or tail. It passed too quickly for detailed study, leaving behind only questions and theories, a mystery that arrived unannounced and departed without answers. A visitor that changed everything and revealed nothing. Comet Borisov carried water from another star system into our own. 2 years after Oumuamua, another interstellar visitor arrived, a comet named Borisov after the amateur astronomer who discovered it. Clearly a comet this time with a visible tail of gas and dust streaming behind it as it swung around the sun, carrying ice and water from some distant star system into the heart of our own solar neighborhood. Analysis of the comet's composition revealed that its water and other ices were similar to what we find in our own solar system, suggesting that the chemistry of planet-forming disks may be universal, the same molecules drifting around young stars everywhere in the galaxy. Unlike Oumuamua, Borisov behaved exactly as a comet should, sublimating its ices as it warmed, producing a coma and tail that allowed scientists to study its makeup in detail before it departed back into interstellar space, carrying with it the memory of whatever star it once called home. It was a gift from the unknown, a sample of another solar system delivered to our doorstep, water from distant suns. And yet the objects that drift between the stars are not always wanderers, for in the very birthplaces of solar systems, new worlds are coming into being. Protoplanetary disks are the dusty cradles where planets are born. Around nearly every young star there swirls a protoplanetary disk, a flattened platter of gas and dust left over from the star's formation, orbiting the newborn sun and slowly clumping together under gravity, collisions, and electrostatic forces to form the seeds of future planets. These disks can span hundreds of times the distance between Earth and the Sun, containing enough material to build multiple worlds, their particles ranging from microscopic dust grains to pebbles to the growing cores of protoplanets, all embedded in a sea of hydrogen and helium that will eventually be blown away by the star's radiation and winds. The process of planet formation takes millions of years, a slow accumulation of matter punctuated by collisions and migrations, yet the disks themselves are visible around distant stars, rings and gaps hinting at the hidden architecture of solar systems still under construction. They are the nurseries of worlds like our own dusty cradles orbiting infant suns, where the story of every planet begins. Gaps in protoplanetary disks reveal the shadows of forming worlds. When astronomers image protoplanetary disks around young stars, they often see concentric rings and dark gaps, structures carved into the dust by the gravitational influence of planets that are in the process of forming. worlds still too small and dim to be seen directly, but massive enough to clear lanes in the surrounding material, leaving shadows where future orbits will lie. Each gap marks the path of a protoplanet, sweeping up dust and pebbles as it travels, growing larger with every orbit, its gravity shaping the disk from which it was born in a slow dance of accumulation that will eventually produce a fully formed world. These observations have revolutionized our understanding of planet formation, revealing that the process begins earlier and proceeds more rapidly than previously believed, with planets taking shape while their parent stars are barely a few million years old. The gaps are windows into the past, showing us how our own solar system might have looked long before Earth existed, shadows pointing toward future worlds. Stellar nurseries glow with the light of thousands of stars being born. Scattered across the Milky Way are vast clouds of hydrogen gas and dust, regions so cold and dense that gravity can overcome the pressure keeping them expanded, causing them to collapse inward in a slow cascade of fragmentation that gives birth to hundreds or thousands of stars at once, lighting up the surrounding nebula with their combined glow. These stellar nurseries are some of the most beautiful objects in the night sky, pillars and swirls of glowing gas illuminated by the fierce radiation of the newborn stars within, their colors revealing the chemistry of the material from which future planets will be made. The process is ongoing even now, with stars being born at this moment in regions like the Orion Nebula, visible on clear winter nights as a faint smudge in the Sword of Orion, a nursery 400 light-years away where our descendants may one day find planets of their own. They are the factories of the galaxy, producing new suns without pause, creation written in light and dust. The pillars of creation stretch 4 light-years tall as incubators of stars. Within the Eagle Nebula, some 7,000 light-years from Earth, rise the pillars of creation, towering columns of interstellar gas and dust that stretch 4 light-years from base to tip, dense enough to resist the radiation of nearby stars and shield the star-forming regions within, incubators of new suns hidden from view by curtains of opaque material. The pillars are being slowly eroded by the ultraviolet light of massive young stars nearby, sculpted into their dramatic shapes by the same forces that will eventually destroy them entirely, leaving behind only the stars that formed within their protective embrace. Images of the pillars have become iconic, representing both the beauty and the impermanence of cosmic structures, monuments that will not survive in their current form for more than another million years or so, a blink in geological time, yet an eternity in human terms. They are cathedrals of creation, standing briefly against the forces that shaped them, temporary grandeur on a cosmic scale. The Carina Nebula hosts some of the most massive stars known to exist. The Carina Nebula is one of the largest and most active star-forming regions in the Milky Way, a glowing expanse of gas and dust spanning over 300 light-years, within which are embedded some of the most massive and luminous stars ever observed, giants that outweigh our Sun by 100 times or more and pour out radiation fierce enough to sculpt the surrounding nebula into twisted pillars and glowing ridges. The most famous of these is Eta Carini, a binary system so unstable that it has undergone dramatic eruptions in the past, briefly becoming one of the brightest stars in the sky during the 19th century, and it is expected to explode as a supernova or even a hypernova within the next few 100,000 years, an event that will be visible from Earth even in daylight. The nebula itself is a laboratory for studying the extremes of stellar physics, a place where the largest stars live fast and die young, scattering their material across space to seed the next generation. A furnace of giants burning without restraint. And as new stars are born, old ones die, leaving behind glowing shrouds that hang in space like the echoes of their final breath. Planetary nebulae are the glowing shrouds of dying sun-like stars. When a star like our Sun reaches the end of its life, it sheds its outer layers in a slow, beautiful exhalation, the stellar winds pushing the gas outward, while the hot core at the center illuminates the expanding shell from within, creating a planetary nebula, a term that has nothing to do with planets, but was chosen by early astronomers who mistook these round, glowing objects for distant worlds. Each planetary nebula is unique, shaped by the rotation, magnetic field, and binary companions of the dying star, some appearing as perfect spheres, others as butterfly wings, hourglasses, or tangled filaments, their colors revealing the elements they contain: oxygen glowing green and blue, nitrogen red, hydrogen pink. Over tens of thousands of years, these shells expand and fade, dispersing into the interstellar medium, enriching the galaxy with the products of stellar nucleosynthesis, the elements that will one day become new stars, planets, and perhaps life. They are the final gifts of dying suns, beauty drawn from ending, a last exhalation before silence. The Helix Nebula is sometimes called the Eye of God. Just 700 light-years from Earth lies the Helix Nebula, one of the nearest planetary nebulae to our solar system, a vast ring of glowing gas expelled by a dying star that now appears in images as a great cosmic eye, its central white dwarf, like a pupil, surrounded by layers of luminous material that suggest an iris gazing outward across the heavens. The nickname Eye of God captures the eerie beauty of this object, though of course it is merely the chance alignment of expanding gas shells and the perspective from which we observe them, art created by physics rather than intention, yet no less striking for its accidental nature. The helix spans nearly 6 light-years across, large enough that if placed at the distance of the nearest star, it would cover more than half the sky, a testament to the scale of stellar death even for a modest star like the one that created it. It is a reminder that our own sun will one day produce a similar shroud. The Eye watches, indifferent and eternal. The Cat's Eye Nebula displays concentric shells of expelled stellar material. The Cat's Eye Nebula is one of the most structurally complex planetary nebulae known, its central region filled with concentric shells, jets, and knots of gas that suggest the dying star at its heart did not shed its material smoothly, but in a series of pulsations and eruptions, each one leaving behind a distinct layer like the rings of a tree recording seasons of growth. These shells are expanding at different speeds, colliding with one another and with the surrounding medium, heating the gas and producing the intricate patterns visible in telescopic images, a record of the star's final convulsions written in glowing hydrogen and nitrogen. The central star itself is exceptionally hot, tens of thousands of degrees hotter than our sun, ionizing the surrounding gas and making it glow with colors that reveal the chemistry of stellar death. The Cat's Eye is a puzzle still being solved, each observation adding detail to the story of how stars end their lives, layers of history written in light. The Butterfly Nebula's wings glow at over 200,000 degrees. The Butterfly Nebula earns its name from the 2 lobes of superheated gas that stretch outward from its central star like the wings of a cosmic insect, glowing at temperatures exceeding 200,000 degrees Celsius, hot enough to emit not just visible light, but intense ultraviolet and X-ray radiation as well. The central star is one of the hottest known white dwarfs, its surface blazing at around 200,000 degrees, its radiation ionizing the surrounding gas and driving it outward at speeds approaching 1,000,000 kilometers per hour, sculpting the bipolar structure that gives the nebula its striking appearance. The wings themselves are torn and ragged, suggesting turbulent winds and magnetic fields that have shaped the outflow into complex filaments, a display of energy that seems almost violent compared to the peaceful image the name evokes. Somewhere within those glowing lobes, the elements forged in the star's core are being scattered into space, destined to become part of future worlds, fire-shaped like delicate wings. The Boomerang Nebula is the coldest known place in the entire universe. 5,000 light-years from Earth lies the Boomerang Nebula, a protoplanetary nebula where gas is being expelled from a dying star at such tremendous speed, approximately 160 kilometers per second, that it has cooled to just 1 degree above absolute zero, making it the coldest known natural place in the entire universe, colder even than the microwave background radiation left over from the Big Bang. This extreme chill arises from the rapid expansion of the outflowing gas, which does thermodynamic work against its surroundings and loses energy, a process similar to the way a refrigerator works, but on an astronomical scale. The nebula appears double-lobed in visible light, its shape giving it the Boomerang nickname, though deeper observations reveal a more complex structure of shells and jets wrapped in the coldest material nature has yet produced. It is a reminder that the cosmos contains extremes in every direction, cold that surpasses imagination. And far beyond the nebulae, the galaxies themselves take on forms both familiar and utterly strange, defying simple classification. Ring galaxies form when one galaxy punches through the center of another. Ring galaxies are among the rarest and most dramatic structures in the observable universe, formed when a smaller galaxy plunges directly through the center of a larger disk galaxy, sending a shockwave of gravitational disturbance rippling outward like the splash from a stone dropped into still water, triggering a ring of intense star formation that expands outward from the point of impact. The collision itself does not destroy the galaxies, for the space between stars is so vast that direct stellar collisions are almost non-existent, but it scrambles orbits and compresses gas clouds, igniting bursts of new stars that trace the expanding ring in brilliant blue light. Some ring galaxies retain a central core where the remnant of the target galaxy's nucleus still sits, while others appear almost hollow, their central regions stripped or disrupted by the passage of the intruder. They are monuments to cosmic violence, beauty forged from collision, ripples frozen in starlight. Hoag's object is a perfect ring of blue stars with an unknown origin. Hoag's object is one of the strangest galaxies known, a nearly perfect ring of young blue stars surrounding a core of older yellow stars, with an almost empty gap between them where very little material seems to exist. A structure so symmetrical and so unusual that astronomers have debated its origin for decades without reaching a definitive conclusion. It does not fit the typical ring galaxy model, as there is no sign of a recent collision, no intruder galaxy visible within or beyond the ring, and simulations have struggled to reproduce its precise geometry through known mechanisms. Some theories suggest it formed through an unusual accretion event, others propose internal instabilities, and still others wonder whether it might be a chance alignment of two unrelated structures viewed from just the right angle. 600 million light-years away, it remains a puzzle, its perfection unexplained, a mystery written in circles of light. The Cartwheel Galaxy expands outward from a cosmic collision. The Cartwheel Galaxy is a textbook example of what happens when one galaxy crashes through the heart of another, its distinctive ring structure expanding outward like the ripple from a cosmic pebble, the shockwave compressing gas and triggering waves of star formation that light up the rim in brilliant blue, while the central hub remains relatively calm, recovering slowly from the disturbance. 500 million light-years from Earth, it was once a normal spiral galaxy before the collision scrambled its structure, and over the next few 100 million years, it will likely return to something resembling its former self as gravity smooths out the disruption. The intruder galaxy is visible nearby, a smaller companion that punched through and emerged on the other side, still traveling away from the scene of the crash. Images of the cartwheel reveal not only the outer ring but inner structures, spokes of material connecting the rim to the hub, ghostly traces of the galaxy's spiral arms reasserting themselves. Chaos slowly remembering order. Irregular galaxies have no defined shape, distorted by collisions and gravity. Not all galaxies fit the neat categories of spirals or ellipses, for many have been so disrupted by gravitational interactions, mergers, or internal dynamics that they have lost any recognizable structure, becoming irregular galaxies, chaotic collections of stars, gas, and dust that sprawl across space without symmetry, without order, without the elegant patterns that grace their more structured cousins. The Magellanic Clouds, visible from the southern hemisphere as fuzzy patches of light, are irregular galaxies orbiting the Milky Way, their shapes pulled and distorted by our galaxy's gravity, their interiors lit by bursts of star formation triggered by the same forces that scramble their structure. Irregular galaxies are common in the universe, especially among smaller systems where the gravitational pull of a nearby giant can overwhelm any attempt at organized rotation. They are the rebels of the galactic zoo, defying classification, beauty without order, life without plan. The Antennae galaxies are two spirals merging into one. 45 million light-years from Earth, two spiral galaxies are locked in a slow-motion collision that began hundreds of millions of years ago and will continue for hundreds of millions more. Their spiral arms stretched into long tidal tails that give them the appearance of an insect's antennae, streams of stars and gas flung outward by the gravitational chaos of the merger. Within the collision zone, clouds of gas are being compressed and heated, triggering an enormous burst of star formation. Thousands of new star clusters blazing into existence in regions where the two galaxies overlap, a fireworks display visible across intergalactic distances. Eventually, the two will merge completely into a single elliptical galaxy, their spiral structures erased, their identities dissolved into a larger whole, but for now they remain distinct, dancers frozen mid-step in a cosmic waltz. This is likely the fate of the Milky Way and Andromeda in a few billion years, two becoming one, slowly and without hurry. The Whirlpool galaxy's elegant spiral arms are visible even in amateur telescopes. The Whirlpool galaxy is one of the most beautiful and best-studied spiral galaxies in the night sky, its graceful arms curving outward from a bright core in a pattern so clear and well-defined that even small telescopes can reveal its structure, making it a favorite target for amateur astronomers and a staple of introductory astronomy courses. Located about 23 million light-years away in the constellation Canes Venatici, it is interacting with a smaller companion galaxy visible at the end of one of its arms, their gravitational dance enhancing the spiral pattern and triggering waves of star formation that light up the arms in blue clusters of young, hot stars. The clarity of its spiral structure has made it a laboratory for studying how density waves propagate through galactic disks, how stars form in response to compression, and how mergers shape the evolution of galaxies over cosmic time. It is a postcard from the cosmos, effortlessly elegant, order written in starlight. I see 11, 1101 could swallow the entire local group of galaxies. IC 1101 is one of the largest known galaxies in the observable universe, a supergiant elliptical galaxy lying over 1 billion light-years from Earth, so vast that it could contain the Milky Way, Andromeda, and every other member of our local group with room to spare. Its diffuse halo of stars extending for millions of light-years across space. It sits at the heart of a massive galaxy cluster, the product of countless mergers over billions of years, each collision adding stars and dark matter to its bulk, growing it into a behemoth that defies easy comparison. Within its boundaries are estimated to be hundreds of trillions of stars, a population so enormous that it exceeds the human capacity for intuitive understanding. Yet the galaxy itself appears almost featureless, a smooth cloud of ancient stars with none of the dramatic spiral arms or dust lanes that make smaller galaxies visually striking. It is size carried to an extreme scale become meaningless, the whale among minnows. The Sombrero Galaxy wears a dark dust lane like the brim of a cosmic hat. The Sombrero Galaxy earns its name from the prominent dark dust lane that encircles its bright central bulge, giving it the appearance of a Mexican hat viewed from the side, one of the most distinctive and recognizable profiles in extragalactic astronomy. Lying about 30 million light-years from Earth, it is technically classified as an unbarred spiral or perhaps a lenticular galaxy, its dust lane hiding regions of ongoing star formation, while the bulge above glows with the light of older, redder stars, a contrast that makes it visually arresting in telescopic images. The galaxy also hosts a supermassive black hole at its center, 1 billion times the mass of our Sun, one of the most massive known in any nearby galaxy, quietly anchoring the swirling mass of stars and gas that surrounds it. It is a galaxy that looks like something from human experience, a familiar shape projected onto the infinite, a hat worn by the cosmos itself. Centaurus A carries the remnant of a smaller galaxy it consumed long ago. Centaurus A is the nearest giant elliptical galaxy to Earth, lying just over 10 million light-years away, and its most striking feature is the dark band of dust and gas that cuts across its middle, the remnant of a smaller spiral galaxy that Centaurus A swallowed some hundreds of millions of years ago, its material still settling into the larger galaxy's gravitational embrace. From its center, a supermassive black hole shoots twin jets of plasma outward for millions of light-years, visible in radio wavelengths as lobes of emission that dwarf the visible galaxy itself, evidence of violent activity fueled by the ongoing digestion of interstellar gas. The galaxy is a laboratory for studying what happens after a galactic merger, how the debris organizes itself over time, how star formation is triggered or suppressed, and how the central black hole responds to the influx of new material. It is a cannibal still digesting its meal, a slow process watched across millions of years, one galaxy wearing another like a scar. And as galaxies drift and merge across the eons, you rest here, still and safe. Let the weight of the cosmos pass over you like a wave passing through water. You need not hold any of it. Let go and breathe. Active galactic nuclei are powered by matter falling into supermassive black holes. At the centers of many galaxies, there lies not a quiet core, but an active galactic nucleus, a region where a supermassive black hole is actively feeding on surrounding gas and dust, its accretion disk glowing so brightly that it can outshine all the stars in its host galaxy combined, radiating across the entire electromagnetic spectrum from radio waves to gamma rays. The energy comes from the gravitational potential of matter spiraling inward, heating to millions of degrees before crossing the event horizon and vanishing forever, a process so efficient that it converts a significant fraction of the infalling mass directly into radiation. These active nuclei vary in intensity, from the modest glow of a Seyfert galaxy to the blinding fury of a quasar, all powered by the same fundamental mechanism, but at different scales and from different angles. They are the feeding times of the universe's largest predators, visible across billions of light years, hunger made luminous. Seyfert galaxies have cores that outshine all their other stars combined. Seyfert galaxies are spiral galaxies with unusually bright central regions, their nuclei blazing with light that can exceed the combined output of all the billions of ordinary stars in the rest of the galaxy, a telltale sign that something extraordinary is happening at the very center, something far more luminous than stellar processes alone can explain. The source is an active supermassive black hole, surrounded by an accretion disk of superheated material, its radiation ionizing the gas clouds nearby and producing the distinctive emission lines that astronomers use to identify Seyfert galaxies in surveys of the distant universe. They are relatively common, found in perhaps 10% of all spiral galaxies, suggesting that the active phase is temporary. A galaxy might spend some periods feeding its black hole intensely and other periods in relative quiescence, cycling between active and quiet states over millions of years. They are galaxies caught in the act, their centers announcing what lurks within, light born from the edge of darkness. LINAR galaxies emit spectra that puzzle even experienced astronomers. LINAR stands for Low Ionization Nuclear Emission Line Region, a type of galactic spectrum that shows emission lines from gas ionized to an unusually low degree, weaker than the high ionization lines seen in Seyfert galaxies, yet still present in amounts too large to be easily explained by normal stellar populations, leaving astronomers uncertain about what exactly powers these faint nuclear glows. Some LINARs may host weakly active black holes, feeding at low rates that produce only modest ionization, while others might be explained by shocks from outflowing gas, post-main sequence stars ionizing their surroundings, or a combination of these effects working together in ways that remain unclear. They are frustratingly common, found in perhaps half of all nearby galaxies, yet their diversity suggests that the label may encompass several distinct physical phenomena lumped together for convenience rather than understanding. They remind us that classification is the beginning, not the end, of knowledge, puzzles hiding in plain sight. And beyond the galaxies themselves, the largest structures in the universe begin to emerge, patterns woven from darkness and light. Galaxy clusters bind thousands of galaxies together in seas of superheated gas. Galaxy clusters are the largest gravitationally bound structures in the universe, collections of hundreds or thousands of galaxies held together by gravity and embedded in vast clouds of superheated gas that glow brightly in X-rays. The gas itself far more massive than all the visible galaxies combined, heated to tens of millions of degrees by the energy released as it falls into the cluster's gravitational well. The galaxies within jostle and interact, occasionally merging, their paths tracing complex orbits within the cluster's embrace, while the hot gas between them radiates energy into space and gradually cools over billions of years. At the heart of many clusters sit giant elliptical galaxies, the cannibalized remains of countless smaller systems that have fallen in and merged over cosmic time, their growth fed by the cluster's inexhaustible supply of victims. These structures take billions of years to form and will persist for billions more, gatherings held together by invisible threads. The Virgo cluster contains over 1,000 galaxies across 15 million light-years. The Virgo cluster is the nearest large galaxy cluster to the Milky Way, lying roughly 54 million light-years away in the direction of the constellation Virgo, a sprawling collection of over 1,000 galaxies spread across a region some 15 million light-years in diameter. Its gravitational influence shaping the motions of galaxies throughout the local universe. At its center lies a giant elliptical galaxy called Messier 87, famous for the supermassive black hole at its heart, one of the first black holes ever imaged directly, and for the relativistic jet of plasma shooting outward from its core, visible even in modest telescopes as a faint spike of light. The Virgo cluster is slowly pulling the Milky Way toward it, adding its gravity to the general expansion of the universe, and in the far future, our local group may eventually merge into its embrace. It is our nearest galactic metropolis, a city of suns, a destination we approach without choice. Galaxies in the Coma cluster are packed so tightly that collisions are inevitable. The Coma cluster is one of the densest galaxy clusters known, containing over 1,000 large galaxies and countless dwarf systems packed into a volume just a few million light-years across, so crowded that gravitational interactions and outright collisions are commonplace, stripping gas from galaxies, triggering bursts of star formation, and gradually transforming spirals into ellipticals as their delicate structures are disrupted by repeated encounters. Unlike the emptier reaches of intergalactic space, where galaxies can drift for billions of years without ever meeting a neighbor, the Coma cluster is a chaotic arena, its members constantly jostling and interacting, their fates intertwined by proximity and gravity. The cluster is permeated by hot gas visible in X-rays, materials stripped from galaxies that have passed through the cluster core, building a reservoir of intergalactic plasma that will take billions of years to cool. It is a cosmic crowd, busy and restless, galaxies too close to ignore each other. Superclusters are the largest known structures in the entire universe. Superclusters are the grandest structures the universe has produced, vast assemblies of galaxy clusters, groups, and filaments stretching across hundreds of millions of light-years, networks of matter woven through the cosmic web like threads in an unimaginably vast tapestry. Unlike galaxy clusters, which are gravitationally bound and will persist forever, superclusters are not bound, their components slowly drifting apart under the accelerating expansion of space, destined to separate over billions of years until each cluster becomes an island universe, isolated from its former neighbors by ever-growing gulfs of emptiness. Mapping these structures has revealed the largest patterns in existence, walls and filaments of galaxies surrounding vast voids, a foam-like architecture that arose from tiny fluctuations in the density of matter in the early universe, amplified over cosmic time by gravity into the structures we see today. They are the bones of the cosmos, visible only from the greatest distances, architecture written across the heavens. The Laniakea supercluster is our cosmic home, spanning 500 million light-years. The Laniakea supercluster, whose name means immense heaven in Hawaiian, is the supercluster to which our own Milky Way belongs, a vast structure spanning some 500 million light-years and containing over 100,000 galaxies, all flowing together toward a gravitational anomaly called the Great Attractor, located near the cluster's center. Mapping Laniakea required measuring not just the positions of galaxies, but their motions, tracing the flow of matter through the cosmic web to identify which galaxies are falling toward the same point and which are drifting away. A painstaking process that only became possible with modern surveys and computational techniques. Our position within Laniakea is peripheral, near the edge, where its influence blends into that of neighboring superclusters, but we are nonetheless part of this immense structure, connected by gravity to galaxies hundreds of millions of light-years from our own. It is our extended cosmic neighborhood, home on the largest scale we know. The Shapley concentration may be pulling our entire region of space toward it. Beyond the Great Attractor lies an even larger accumulation of matter, the Shapley concentration, a vast supercluster complex located some 650 million light-years from Earth. So massive that its gravitational pull is felt across a significant fraction of the observable universe, drawing galaxies and clusters toward it like water flowing downhill toward a basin. The Shapley concentration contains dozens of galaxy clusters packed into a relatively small volume of space, a density of matter far exceeding the cosmic average, and its influence combines with the Great Attractor to shape the motions of galaxies throughout our region of the cosmos. Our own Milky Way, along with the Virgo cluster and the entire Laniakea supercluster, is slowly drifting in the direction of this immense mass concentration, though the journey will take billions of years and may never be completed as cosmic expansion accelerates. It is a tide pulling the universe toward a distant shore, motion without awareness. And between these vast structures, there exist regions of almost pure emptiness, places where few galaxies dare to form. Cosmic voids stretch over 100 million light-years, nearly empty of galaxies. Between the filaments and walls of galaxies that make up the cosmic web, there exist vast cosmic voids, regions of space that can stretch over 100 million light-years in diameter, yet contain only a tiny fraction of the galaxies that would be expected if matter were distributed uniformly, emptiness on a scale that dwarfs anything else in the universe. These voids are not truly empty, for they contain dark matter in diffuse halos and a thin scattering of dwarf galaxies, but compared to the packed clusters and dense filaments that surround them, they are islands of almost nothing, places where gravity had slightly less to work with in the early universe and structure formation proceeded more slowly. Over time, voids grow as matter flows out of them toward denser regions, expanding and merging with neighboring voids, sculpting the foam-like architecture of the cosmos. They are absences that define the whole, space becoming emptier as time passes. The Boötes void contains far fewer galaxies than surrounding space suggests. The Boötes void is one of the largest known voids in the universe, a roughly spherical region of space about 330 million light-years in diameter, containing only about 60 galaxies, where thousands would be expected if matter were distributed uniformly, an emptiness so extreme that it has sparked speculation about its origins and nature. Early surveys found it nearly devoid of galaxies, leading to nicknames like the Great Void, and subsequent observations have confirmed that while it is not perfectly empty, it remains one of the most underdense regions of space ever mapped. Some have wondered whether the void might be artificial, cleared by some unimaginable technology, though the natural processes of cosmic structure formation are more than sufficient to explain its existence. It is a reminder that the universe is as much absence as presence, a place where silence has volume. Even cosmic voids contain thin tendrils of dark matter and lonely galaxies. Although cosmic voids are defined by their emptiness, they are not absolutely devoid of matter, for thin tendrils of dark matter thread through their interiors, connecting the denser regions on opposite sides, and within these faint filaments, a scattering of galaxies can be found, lonely outposts far from the bustling clusters and rich filaments that characterize the densest parts of the cosmos. These void galaxies tend to be small and relatively isolated, their star formation often proceeding at leisurely rates due to the lack of gas-rich neighbors or disruptive interactions, evolving in quiet solitude over billions of years. Studying them offers insights into how galaxies develop without the complications of crowded environments, natural laboratories for understanding the simplest pathways of galactic evolution. They are hermit galaxies, dwelling in the spaces between communities, content in solitude, stars burning alone in emptiness. And this unseen substance, dark matter, shapes the very skeleton of the cosmos, though we have never seen it directly. Dark matter reveals itself only through gravity, never through light. Dark matter is one of the most profound mysteries of modern astrophysics, a substance that makes up roughly a quarter of the universe's total energy content, yet has never been directly detected, revealing its presence only through the gravitational effects it has on visible matter, bending light, speeding up galaxy rotations, and providing the scaffolding on which ordinary matter accumulates to form galaxies and clusters. It does not emit, absorb, or reflect light of any wavelength, passing through ordinary matter like a ghost through a wall, interacting only through gravity and perhaps through forces so weak that our detectors have not yet been sensitive enough to register them. Despite decades of searching, no dark matter particle has been identified in laboratory experiments, though the evidence for its existence from astronomical observations is overwhelming, a paradox that drives some of the most ambitious physics experiments on Earth. It is the invisible majority, shaping everything we see while remaining unseen, gravity without a source. Halos of dark matter extend far beyond every visible galaxy. Every galaxy is embedded within a halo of dark matter, an invisible sphere of this mysterious substance that extends far beyond the visible stars and gas, sometimes 10 times farther than the luminous disk or bulge, containing most of the galaxy's total mass, even though it produces no light at all. These halos are inferred from the motions of stars and gas at the outskirts of galaxies, which orbit faster than the visible mass alone could explain, and from gravitational lensing, where background objects are distorted by the combined mass of the visible and invisible components. Without their dark matter halos, galaxies would not have formed in the first place, for ordinary matter alone could not have collapsed quickly enough in the early universe to build the structures we see today, and the halos continue to shape galactic dynamics long after formation is complete. They are cocoons of gravity, embracing every visible star, a presence felt but never seen. The cosmic web connects galaxy clusters across billions of light years. The cosmic web is the largest structure in the universe, a network of dark matter filaments and ordinary gas that connects galaxy clusters across billions of light years, forming a vast, three-dimensional lattice within which galaxies are merely the luminous nodes, the bright points marking where the invisible threads intersect. This web arose from tiny fluctuations in the density of the early universe, regions slightly denser than average that grew under the influence of gravity, pulling matter toward them and creating the filaments and nodes we observe today, while the underdense regions expanded into the voids that make up most of the cosmic volume. Observing the web directly is difficult because the filaments are faint, their gas heated but diffuse, yet techniques like studying the absorption of light from distant quasars have revealed the structure in ever greater detail. It is the scaffold of everything, the pattern underlying reality. Gravitational lensing bends light around invisible masses of dark matter. Gravitational lensing is one of the most powerful tools astronomers have for detecting dark matter. a phenomenon predicted by Einstein's theory of general relativity, in which massive objects warp the fabric of spacetime so much that light passing nearby is bent, following curved paths as if deflected by an enormous invisible lens. When a galaxy cluster lies between Earth and a more distant galaxy, the cluster's gravity can magnify, distort, and sometimes multiply the background galaxy's image, creating arcs, rings, and multiple copies of the same object, a visual signature of the mass causing the deflection. By analyzing the degree and pattern of distortion, astronomers can map the distribution of mass in the lens, revealing dark matter that would otherwise be completely invisible, tracing its presence through its influence on light. This technique has confirmed that dark matter exists and is distributed in halos and filaments just as models predict. The invisible made visible through geometry. The Bullet Cluster shows dark matter passing through colliding galaxies separately. The Bullet Cluster is one of the most important objects in modern cosmology, a pair of galaxy clusters that collided and passed through each other roughly 150 million years ago, leaving behind a striking separation between the hot gas, which was slowed by friction and remains clumped in the middle, and the dark matter, which passed through without interacting and now lies on opposite sides, traced by gravitational lensing of background galaxies. This separation provides direct observational evidence that dark matter is real and distinct from ordinary matter. For if the mass responsible for the lensing were simply hidden gas, it would have been slowed along with the visible hot plasma, but instead, it moved through the collision like a ghost through a wall, its gravity unimpeded by friction. The Bullet Cluster has become a standard reference whenever the existence of dark matter is debated, a cosmic experiment that nature performed for us. Two masses passed through each other and emerged distinct. And alongside dark matter, an even more mysterious force fills the universe, pushing it apart at an ever-increasing rate. Dark energy drives the accelerating expansion of space itself. Dark energy is the name given to whatever is causing the expansion of the universe to accelerate, a discovery made in 1998 by astronomers studying distant supernovae, who found that the universe is not slowing down, as one might expect if gravity were the only force at play, but speeding up, driven by something that acts like a repulsive pressure filling all of space. It makes up nearly 70% of the total energy content of the cosmos, yet we have no idea what it is, where it comes from, or whether it will continue to behave in the same way as the universe ages. Some theories treat it as a property of space itself, a cosmological constant that Einstein introduced and later regretted, while others suggest it is a dynamic field that changes over time, with implications that differ dramatically depending on which is correct. It is the dominant component of the universe, the force of emptiness itself. No one knows what dark energy truly is or where it comes from. Despite its dominance in the energy budget of the universe, dark energy remains utterly mysterious, its nature unknown, its origin unexplained, its future behavior unpredictable, a blank space on the map of physics where our theories simply fail to reach. Some physicists believe it might be the quantum vacuum, the energy of empty space predicted by quantum field theory, but the predicted value is wildly different from what is observed, a discrepancy of 120 orders of magnitude that has been called the worst prediction in the history of physics. Others propose new fields, new particles, or modifications to gravity itself, but none of these alternatives has been confirmed, and all face their own difficulties in matching the observations. Dark energy is a riddle without a satisfactory answer, the universe propelled by something we cannot name. The Great Attractor pulls thousands of galaxies toward a hidden region. In the direction of the constellations Centaurus and Norma, lies the Great Attractor, a gravitational anomaly that is pulling the Milky Way and thousands of other galaxies toward it at hundreds of kilometers per second. A flow of matter on a scale that was first noticed decades ago, but whose precise nature remained hidden for years, because the region lies behind the dense star fields of the Milky Way's disk, where dust and gas obscure our view. Modern observations, particularly in infrared and X-ray wavelengths that can penetrate the intervening material, have revealed that the Great Attractor corresponds to a concentration of mass centered on the Norma cluster, a relatively modest galaxy cluster that nonetheless contributes, along with surrounding structures, to the gravitational pull felt throughout our region of the cosmos. It is not a single object, but a locus of influence, a direction in which the universe is falling. Motion toward a hidden center. Dark flow suggests galaxies may be moving toward something beyond the observable universe. In 2008, some astronomers reported evidence for what they called dark flow, a coherent motion of galaxy clusters toward a particular spot in the sky that could not be explained by the distribution of mass within the observable universe, suggesting that something beyond the cosmic horizon, beyond the limits of what we can ever see, might be exerting a gravitational pull on everything within our view. If real, dark flow would imply that the universe is far from uniform on the largest scales, that structures or conditions beyond the horizon are affecting what happens within it, a radical departure from the standard cosmological model that assumes isotropy and homogeneity on sufficiently large scales. The claim remains controversial, with some analyses supporting it and others finding no significant evidence, and the debate continues as larger surveys gather more data. It is a question about what lies beyond the edge of the known, a pull from the unseen. And even the light that fills the space between the stars carries mysteries, remnants of the earliest moments of creation. The cosmic microwave background is light from the very beginning of time. The cosmic microwave background is the oldest light in the universe, a faint glow filling all of space that originated just 380,000 years after the Big Bang, when the hot plasma that permeated the early cosmos cooled enough for electrons and protons to combine into neutral hydrogen, freeing light to travel unimpeded through space for the first time. This light has been traveling ever since, stretched by the expansion of the universe from the intense heat of its origin to the frigid microwave wavelengths we detect today, a remnant radiation with a temperature of just under 3 degrees above absolute zero, remarkably uniform in every direction, yet containing tiny fluctuations that reveal the seeds of all future structure. Studying the cosmic microwave background has allowed cosmologists to measure the age, composition, and geometry of the universe with extraordinary precision, confirming predictions of the Standard Model and revealing details about the earliest moments. It is the baby picture of the cosmos, light older than all the stars. Tiny fluctuations in ancient light reveal the seeds of every galaxy. The cosmic microwave background is not perfectly smooth, but contains tiny fluctuations in temperature, variations of just a few hundred thousandths of a degree from one patch of sky to another. And these minuscule differences represent the density variations in the early universe that would eventually grow under gravity into the galaxies, clusters, and cosmic web we observe today. Where the ancient light is slightly warmer, matter was slightly denser, and where it is slightly cooler, matter was slightly less concentrated, a pattern frozen into the light when it was released and preserved across nearly 14 billion years of cosmic expansion. These fluctuations encode information about the physics of the early universe, the balance of matter and radiation, the geometry of space, and perhaps even the mechanisms that generated the initial perturbations in the first fractions of a second after the Big Bang. They are fossils of the primordial conditions, the fingerprints of creation. The cold spot remains one of the most debated features in the cosmic sky. The cold spot is a region of the cosmic microwave background that appears significantly colder than its surroundings, a patch of sky spanning several degrees in the southern constellation Eridanus that has prompted decades of debate about its origins, whether it is a statistical fluke, the imprint of an unusually large cosmic void, or evidence for physics beyond the standard model. Some analyses suggest it corresponds to an enormous supervoid in the distribution of galaxies, a region so empty that light passing through it loses energy as space expands, emerging cooler than light that traversed denser paths. Yet this explanation may not fully account for the observed temperature difference. Others have proposed more exotic explanations, including the possibility that the cold spot marks a location where our universe interacted with another, a kind of cosmic bruise left by a collision with an adjacent domain of reality. It is an anomaly that refuses easy explanation, mystery painted in microwave light. The cold spot could be the imprint of another universe pressing against our own. Among the more speculative explanations for the cold spot is the idea that it might be a scar left by a collision between our universe and another, a neighboring pocket of space-time that bumped against ours in the earliest moments of cosmic history, leaving an imprint that persists to this day as a subtle temperature anomaly in the microwave background. This hypothesis arises from theories of eternal inflation, which suggest that our universe is just one bubble among countless others, each with its own properties, born from a larger inflationary process that continues forever, occasionally producing collisions where two bubbles touch. If such collisions happened, they would leave characteristic signatures in the cosmic microwave background, rings or spots where the physics was perturbed by the contact, and some researchers have claimed to see hints of such features, though the evidence remains ambiguous. It is a door to the multiverse, possibly ajar, a glimpse of what might lie beyond. And as the echoes of creation drift quietly through the darkness, you too drift, softly, gently. Let your breath become as steady as the pulse of distant light. Let your body become as still as the spaces between the stars. Rest. Cosmic strings may be thinner than an atom, yet heavier than a mountain range. Cosmic strings are hypothetical defects in space-time, infinitely long or looped threads of concentrated energy left over from phase transitions in the early universe, relics of the moments when the forces of nature, separated from their unified state and imperfections, froze into the fabric of reality like cracks in ice. If they exist, these strings would be thinner than the width of an atom, yet so dense that a single centimeter of string could weigh as much as a mountain range, stretching across the cosmos at significant fractions of the speed of light, their immense tension keeping them taut against the expansion of space. They would bend light like gravitational lenses, creating distinctive signatures that astronomers have searched for without definitive success, and their oscillations would generate gravitational waves detectable by future observatories more sensitive than those operating today. They remain theoretical, predicted but unconfirmed, tantalizing hints at physics beyond the standard model, threads of the ancient cosmos. A passing cosmic string would create double images of stars behind it. If a cosmic string passed between us and a distant star or galaxy, its intense gravity would bend light around it from both sides simultaneously, creating identical double images of the background object, a distinctive lensing signature quite different from the arcs and distortions produced by galaxy clusters or dark matter concentrations. Unlike ordinary gravitational lenses, which produce magnification and distortion along with image multiplication, a cosmic string would split the image cleanly, producing two copies with nearly identical brightness and no significant stretching, a fingerprint that would be difficult to explain by any other mechanism. Astronomers have searched for these telltale doubles in surveys of distant quasars and galaxies, so far without finding definitive evidence, leaving the existence of cosmic strings an open question. The search continues, for a single confirmed detection would revolutionize our understanding of the early universe, a split image pointing to unity. Domain walls are vast sheets of energy left over from cosmic phase transitions. Domain walls are another type of topological defect predicted by particle physics, vast two-dimensional sheets of concentrated energy that would form when the early universe underwent symmetry-breaking phase transitions, boundaries between regions where a field settled into different stable states, like the walls between magnetic domains in a piece of iron, but stretched to cosmic scales. If they exist in significant numbers, domain walls would have dramatic effects on the expansion and structure of the universe, contributing energy density and potentially dominating the cosmic budget, which observations suggest has not happened, leading most cosmologists to conclude that any domain walls that formed were either unstable or connected to strings and quickly dissipated. The constraints from cosmology are tight, but exotic models still allow for domain walls in corners of the universe where we might not yet have looked. They are ghosts of symmetry breaking, boundaries without substance, walls that divide nothing from nothing. And from the theoretical to the observed, the strangest signals continue to arrive from the depths of space, baffling and delighting astronomers in equal measure. Tabby's star dimmed in patterns that no natural process could fully explain. Tabby's star, officially known as KIC 8,462,852, captured worldwide attention when the Kepler Space Telescope observed it dimming in irregular, unpredictable patterns, sometimes by as much as 20%, far more than any known planet or natural phenomenon could easily explain, leading to speculation that ranged from swarms of comets to megastructures built by alien civilizations. The star lies about 1,500 light-years from Earth, an F-type star slightly hotter and more massive than our Sun, and its dimming events have been monitored intensively ever since the initial discovery, with each new observation adding data without fully resolving the mystery. Most astronomers now favor natural explanations, perhaps dust clouds, disrupted comets, or material from a consumed planet, but the precise mechanism remains elusive. Whatever the cause, Tabby's star has become a symbol of the unexpected wonders that systematic observation can reveal, a riddle still waiting for its answer. The WOW signal lasted 72 seconds and has never repeated. In 1977, a radio telescope in Ohio detected a narrowband signal from the direction of the constellation Sagittarius that was so unusual, so unexpectedly strong, that the astronomer who discovered it wrote WOW in the margin of the printout, giving the signal its enduring name and launching decades of speculation about its origins. The signal lasted 72 seconds, the maximum duration the telescope's design would allow for a fixed-point source as the Earth rotated, and it has never repeated despite extensive follow-up observations with more sensitive instruments, leaving its source entirely unknown. Natural explanations have been proposed, including comets, interstellar clouds, and instrumental artifacts, but none has been confirmed, and some researchers continue to entertain the possibility that it was an artificial signal, a brief hello from an intelligence somewhere among the stars. It is a single data point, insufficient for conclusions, yet too intriguing to forget. A shout from the void, heard once and never again. Przybylski's star contains elements that should not exist in stellar atmospheres. Przybylski's star is one of the most chemically peculiar stars known, its spectrum revealing the presence of elements that should not exist in significant quantities in any stellar atmosphere, short-lived radioactive elements like actinium, protactinium, and neptunium that decay too quickly to have survived from the star's formation and must be continually produced or supplied by some ongoing process. Located about 370 light-years from Earth, it is classified as an app star, a type known for strong magnetic fields and chemical peculiarities. But even among app stars, it stands out for the sheer strangeness of its composition. Theories to explain its spectrum include unusual nucleosynthesis in the star's interior, accretion of exotic material from an unseen companion, or the presence of super-heavy elements decaying through chains that produce the observed signatures. No explanation has been universally accepted, and the mystery persists, a star that refuses to fit the models, chemistry that should not exist. SDVE is a purple ribbon of light first documented by amateur sky watchers. SDVE is an atmospheric phenomenon that appears as a narrow ribbon of purple and green light stretching across the sky, first brought to scientific attention by amateur aurora photographers who noticed it appearing alongside the northern lights, but distinct from the typical auroral curtains, prompting researchers to investigate and eventually recognize it as a previously undocumented type of optical emission. The name originally stood for Strong Thermal Emission Velocity Enhancement, a backronym fitted to the whimsical name chosen by the citizen scientists who first catalogued it, and subsequent studies have confirmed that it arises from a different mechanism than traditional aurorae, involving fast-flowing rivers of hot gas in the ionosphere rather than the particle precipitation that causes ordinary auroral displays. SDVE appears at lower latitudes than typical aurorae and lasts for shorter periods, a fleeting visitor that requires clear skies and good timing to observe. It is a reminder that the sky still holds surprises, discovery shared between professionals and dreamers. And finally, we turn to the objects that remain at the very frontier of what is known, where science and wonder become indistinguishable. White holes would let matter and light escape, but never enter. White holes are the time-reversed counterparts of black holes, solutions to Einstein's equations of general relativity that describe regions of space-time from which matter and light can escape, but into which nothing can ever enter, a cosmic one-way door opening outward rather than inward. While black holes are observed throughout the universe, white holes exist only in theory, for no mechanism has been proposed that could create them. And if they ever did form, they would be unstable against any incoming matter, which would violate the very condition that defines them and likely transform them into something else. Some speculative theories suggest that white holes might appear at the other end of black holes, perhaps in other universes or other regions of our own, or that they might explain certain transient phenomena like gamma-ray bursts, but these ideas remain firmly in the realm of conjecture. They are mirrors of darkness, reflecting possibility rather than light, exits without entrances. Wormholes could connect distant regions of space or even different universes. Wormholes are hypothetical tunnels through space-time, shortcuts that could link distant points in the universe or even connect different universes altogether, allowing travel between regions separated by vast distances in ordinary space, but connected by a much shorter path through the wormhole's throat. They were first described mathematically in the 1930s and have since become staples of science fiction, though no wormhole has ever been observed, and there are serious doubts about whether they can exist in a stable, traversable form, for the physics required to hold one open would involve exotic matter with negative energy, a substance whose existence remains controversial. If they could be created or discovered, wormholes would revolutionize our understanding of space, time, and perhaps causality itself, raising questions about paradoxes and the nature of reality that lie at the frontier of theoretical physics. They are doors that may never open, possibilities written in equations. Naked singularities would be points of infinite density visible to outside observers. A naked singularity is a point of infinite density that is not hidden behind an event horizon, a region where the curvature of spacetime becomes infinite yet remains visible to outside observers, violating the cosmic censorship conjecture that nature always hides singularities behind horizons so that their unpredictable physics cannot affect the rest of the universe. If naked singularities exist, they would challenge our understanding of determinism and causality, for the laws of physics break down at a singularity and cannot predict what will emerge from it, meaning that anything could, in principle, escape into the surrounding universe. Most physicists believe that nature forbids naked singularities, but proving this mathematically has proved elusive, and some solutions to Einstein's equations do seem to allow them under extreme conditions. They are forbidden zones made visible, paradoxes exposed to the cosmos, the universe's deepest secrets laid bare. Planck stars may bounce back from black holes to seed new universes. Planck stars are hypothetical objects proposed as alternatives to the singularities thought to lie at the hearts of black holes, regions where gravity compresses matter to the Planck density, the smallest meaningful scale in physics, at which point quantum gravitational effects become important and may halt the collapse, causing the matter to bounce back outward in a process that could take longer than the current age of the universe as seen from outside, but might be nearly instantaneous from the perspective of the infalling matter. According to some theories, this bounce could seed the formation of a new universe, a baby cosmos born from the death of a black hole in its parent universe, its expansion happening in a different region of space-time inaccessible to us. These ideas lie at the intersection of general relativity and quantum mechanics, where our current theories are incomplete and speculation necessarily fills the gaps. They are births hidden inside deaths, endings that become beginnings. Fuzzballs replace black hole singularities with tangled balls of strings. In string theory, the fundamental constituents of matter are not point particles, but tiny vibrating strings, and when applied to black holes, this perspective leads to the concept of fuzzballs, objects that look like black holes from a distance, but have no singularity or event horizon in the traditional sense, instead consisting of an incredibly tangled ball of strings and higher dimensional objects called brains that fills the entire region where the event horizon would be. The fuzzball picture resolves some of the paradoxes associated with black hole thermodynamics, explaining how information might be preserved rather than lost, and it suggests that the smooth geometry of classical black holes is an approximation that breaks down at the quantum level. These ideas remain highly theoretical, dependent on the validity of string theory itself, which has not yet been experimentally confirmed. They are alternative visions of the dark, fuzzy rather than singular. Tangles replacing infinities. Boson stars are invisible clumps of matter mimicking the appearance of black holes. Boson stars are hypothetical clumps of bosonic matter, particles like photons or hypothetical axions that obey different quantum statistics from the fermions that make up ordinary matter, held together by their own gravity into compact objects that do not emit light and could mimic the observational signatures of black holes without actually possessing an event horizon or singularity. They could, in principle, be as massive as the supermassive black holes thought to lurk at the centers of galaxies, or as light as stellar mass black holes, depending on the mass of the constituent bosons and the amount of matter that has accumulated. Distinguishing a boson star from a black hole would be extremely difficult, requiring observations of phenomena that penetrate or bypass the hypothetical event horizon, and some researchers have proposed that what we call black holes might actually be boson stars or similar exotic objects. They are alternatives to darkness, transparency masquerading as opacity, imposters waiting to be unmasked. And so our journey through the strangest objects in deep space draws softly to a close. From the crushing embrace of black holes to the spinning fury of pulsars, from the cold silence of cosmic voids to the tangled mysteries of dark matter, we have drifted past wonders that bend the mind and stretch the imagination beyond familiar limits. These objects, so distant and so strange, ask nothing from us except perhaps a quiet moment of wonder. If these cosmic curiosities have brought you peace tonight, consider returning for more journeys like this one. Each video is made with care for you and for all the restless souls finding their way here, seeking stillness among the stars. There are always more wonders waiting in the silence. Right now, as you rest, the strange objects we have explored continue their quiet existence. Somewhere in the darkness, a neutron star is spinning, a black hole is whispering radiation into the void, and light from a quasar is crossing the gulf between galaxies. They do not know you are here, and yet you are connected to them, made of the same matter, shaped by the same forces, resting beneath the same vast sky. Let your eyes close if they have not already. Let your breath slow and deepen, becoming as steady and patient as the turning of a distant galaxy. Feel your body grow heavy, sinking deeper into rest, shoulders softening, jaw unclenching, hands falling open. Let go of every thought, every image, every fact you have heard tonight. There is nothing to remember, nothing to hold, just stillness, just rest. Tonight, as you sleep, the cosmos continues its work. Black holes spin, stars collapse and ignite, planets wander through endless night, and somewhere in a nebula no one has yet named, new suns are being born. The universe moves without hurry, without urgency, and so do you. You are a small, warm presence within this vast and silent darkness, peacefully resting among the strangest wonders of creation. Sleep well, sweet dreams, and may you carry with you the quiet knowledge that strangeness is no enemy of peace, but perhaps its truest companion, reminding us that even the unknown can be gentle. This has been Drowsy Discovery. Good night.